All right, let's get going here. So you have homework that's not due for a little while, so we're good to go there. I got all your papers, again, that were due on Wednesday, and I have not looked at them yet. My goal is to get 1 or 2 of them done a day, so hopefully by the end of next week. That's my goal. That's what I would like to get done for papers at this point in time. I don't know, other schedule questions, homework questions, anything, what's coming up, etc. Now's a good time to ask. Anybody anything? Nothing that comes to mind? Okay,
I did put in a proposal for a minor declaration mathematics.
Yes, Dr. Schultz copied us on that, so that should be good. And I don't think I have to sign it. Maybe I do. I'll double check and see. But yes, it came through. So. Everybody good to go with classes for next semester? Registration for you guys who are not graduating is Wednesday at noon, I think. Yes. All right. So again, feel free to email me if you have questions about what classes you should be taking next semester, etc. That is totally fine. Anything else before we jump into what we're doing today? Okay, I'm excited about today because I get to talk about my research, and I don't get to talk about my research all that often, and it is fun. So we will, full screen. There we go, full screen. So this is for a presentation that I gave previously at one of my colleagues' colleges. John has a question first, yes.
Yeah, sorry, I don't want to interrupt, but
You're fine.
I just looked at WLC and registration is today for...
Is it today or is it? Yes, today. I'm sorry. Yes, today's the 20th. I was thinking Wednesday is the 20th. My bad, today. Thank you. Yes. Register at noon. Don't wait till Wednesday. Don't listen to me. I'm losing track of life. Yes. Okay, now that we've gotten that fixed, sorry. So this is for a presentation that I gave one of my colleagues from grad school teaches in Illinois. And so I went down there a couple of times and gave this presentation. That's why it looks a little bit different. I cut some of the stuff out because a lot of it we've talked about already. So there's basic stuff at the beginning, like basics of cryptography and all that fun stuff. Also, the authentication code scenario is review, but since we just talked about that on Friday, I'm gonna run through it quickly as well. And today is totally up to you how much you wanna take notes or not, whatever you want to do. Sorry, I have all my slides and I don't want all of them. Okay, so remember Alice wants to send a message to Bob, Eve wants to disrupt communication, Bob wants to make sure that the message hasn't been changed in transit, all this same stuff. So if you wanna do a message authentication code, secret key, authentication tag, Alice sends both the message and the authentication tag to Bob. Bob gets, we're gonna call this M prime. So he gets some message that hopefully is the same as the message that Alice sent, but he's not sure at this point in time. So he's gonna compute a new authentication tag. We're gonna call it T prime, and he's gonna see if the 2 authentication tags match. So he's getting this new message, which hopefully is the same as the previous one. He's completing this new authentication tag, and he's hoping that they match. This is what we went over last time. Also, what we went over last time is Eve doesn't know K, so she can't compute a tag, and the security is compromised if one of 2 things happens. Either Eve figures out the key, then obviously the security is compromised, or she figures out how to forge authentication tags. So those are the 2 things that will compromise the security. All right, technical definition, family of functions, right? Family of functions. So I'm writing it in set theory notation this time instead of the way that I wrote it on the slides last time, but same idea, family of functions. And you need ease of computation, compression, and computation resistance. So once again, this is the stuff that we talked through on Friday. We did all of this on Friday. We've got all of this. We have this background. All right, here's where my research starts. So we need these things called quasi-groups, all right? Quasi-groups are a set, and by the way, interrupt me at any point in time by doing a virtual hand raise, and I'll be more than happy to answer questions. Quasi-groups, a set and a binary operation. So we've got a set of elements, and then remember, a binary operation takes 2 things as input and gives you 1 thing as output, okay? So binary operation. For those of you who have taken abstract algebra before, this is going to sound a little bit familiar, and we'll make a connection to groups in a minute. But here's your requirements. The first one is called closure, and this should sound super familiar from groups. So basically, if you put in 2 elements of the quasi-group, you get out an element of the quasi-group. We're not taking elements beyond this set. For example, the integers under addition, subtraction, multiplication all have closure. If you add 2 integers, you're gonna get an integer. If you subtract 2 integers, you're gonna get an integer. If you multiply 2 integers, you're gonna get an integer. They do not necessarily have closure under division because 1 divided by 2 is not an integer. So closure just means whatever 2 elements you put in, what the type is, you get an element of that type back out. That's what's going on. And then there's this thing that is horribly convoluted called unique solubility of equations. And if I were teaching an abstract algebra class, we would go way deep into this. There exists these unique X and Y so that this thing happens, yada, yada, yada. But you are cryptographers and you are not algebraists, so we are going to say it in terms of something that you understand. And that is what's called a Latin square. So basically, unique solubility of equations means that when I look at the table for computing this binary operation, I get what's called a Latin square. And you know what a Latin square is if you've done a Sudoku. It has each element once in each row and once in each column, all right? So that is what you have to have for a quasi-group. When you look at the multiplication table, you have to have a Latin square. Here's an example. So let's say that my set is 0 through 7, okay? My elements are 0 through 7. So what I'm gonna do is put the first element that I'm multiplying across the top and the second element that I'm multiplying down the side. All right, and then the stuff in the middle is the answer. So for example, 3 circle 0, can you see my mouse hand? Yes, okay. 3 circle 0 is going to end up being 1. 4 circle 4 is going to end up being 0. 2 circle 6 is 1, but 6 circle 2 is 7. So answers are different depending on what order you put them in. Notice that this represents a quasi-group because 2 things. First of all the elements inside the table are from 0 through 7, right? I didn't introduce any new elements. All the elements are from 0 through 7. And if you look at all the rows and you look at all the columns, each element appears exactly once in each row and in each column, okay? That's your definition of a quasi-group. How are we doing so far? Good? So far, so good? Everybody's good? Okay, I'm getting some nods, that's great. Quick review, for those of you who have had abstract algebra, a group has all of these properties: closure, associativity, identity, and inverses. So all of these properties: closure, associativity, identity, and inverses. And a group is commutative if you can switch the elements around, okay? If this sounds interesting, take abstract algebra. We're offering it in the fall. You can register for it today at noon, as it turns out. So there you go. Comparison. Every group is, in fact, a quasi-group. So every group is a quasi-group, but not every quasi-group is a group. And here's some of the properties that might fail. So a quasi-group is not necessarily associative. In particular, let's just play with an equation here. Remember, associative means you can move the parentheses. So let's see if I can hit one where it's not associative. 2 circle 1 circle 3 is going to be 2 circle 1 gives you 5. And then I want to circle that with 3. So 5 circle 3 is 0. But 2 circle 1 circle 3. Let's do the 1 circle 3 first. 1 circle 3 is 5. That's 2 circle 5, and hopefully, oh good, no, is equal to 0. Okay, well that one didn't work. So that's an example of one associative triple. There's pairs in here, there's triples in here that are not associative. Let me try one more, and if I don't get it to work, we're just going to assume that there are ones that are non-associative. Let me try one more. We'll see if I can hit it for this one. How about 1 circle 2 circle 5, and 1 circle 2 circle 5. Let's see if we can hit this one. 1 circle 2 is 0, circle 5 is 3, and 2 circle 5 is 0. And then 1 circle 0 is 6. 3. 1 circle 0 is 3. Fail. Okay, there really are, I promise, there really are non-associative pairs in here. I'm just not finding one at this particular instant in time. So really do have non-associativity, promise. The other things that you are going to have, and now I need to stop annotating. Daniel, question.
So is that like the analog, is a Latin square like